Alright, today we're going to be going over logarithms, which are a different way of thinking about exponents. Right, so let's start off with a traditional exponent, right? 3 to the 3. That equals 27, right? But let's think about it in a different way. Let's imagine that I have a growth machine where I press a button. I press this button right here, and I immediately get 3 times as big. If I press it once, I'm 3 times as big. If I press it twice, I'm 9 times as big. If I press it 3 times, I'm 27 times as big as I originally was. Right, so in this equation, right, this 3 right here, this base, represents the growth rate, or how many times bigger I get when I press the button. This 3 right here, the exponent, represents the number of times I've pressed that button. And this 27 here, well, that's my final value. That's how many times bigger I've gotten after pressing the button 3 times. Let's apply this to a couple other logarithmic exponential equations. Let's say 3 to the 0, right? But we know anything to the 0 is 1. And this makes sense if we're thinking about a growth machine, right? If I haven't pressed this button, right, I've pressed it 0 times, I'm going to be the same size that I am. I'm going to be 1 times as big as I currently am. So it makes sense that this is equal to 1. What about 3 to the negative 1, right? Well, the properties of exponents tell us that anything raised to the negative power is the same thing as 1 over that value raised to the same positive power, right? So 3 to the negative 1 is the same thing as 1 over 3 to the 1, which is the same thing as 1 over 3. Which makes sense, right? If this is negative, that's kind of like us going back in time. If we go back in time, we're going to be a fraction of our current size. But why did I say all this about growth machines and growth rates? Well, they make it a lot easier to understand what logarithms are. What logarithms tell us is how many times we've pressed that button, right? How many times we've grown by a given growth rate, right? So let's rewrite this equation right here as a logarithm. That's log base 3. I say base 3 because the base in here is 3. Log base 3 of 27 is 3. So I've pressed this button 3 times, each time tripling in size, so I'm 27 times as big, right? I can rewrite this equation as log base 3 of 1 equals 0. How many times do I have to press the button to be 1 times as big as I currently am? Well, 0. I don't have to press the button. I'm already the size that I want. Right, what about this? Log base 3 of 1/3. That equals negative 1. Right? I need to go back in time so that I can be a fraction of my current size. Now let's apply this to a couple logarithms and see how we can solve them and see if we can learn anything else. Right, so let's start off with a pretty simple one. Let's say I want to find log base 2 of 8, right? How many times do I have to press a button and double in my growth machine to be 8 times as big as I currently am? Well, if I double once, I'm 2 times as big. If I double twice, I'm 4 times as big. But if I double 3 times, I'm 8 times as big, right? So I need to double 3 times. I need to press that button 3 times to be 8 times as big, right? Let's do another one. Let's say log base 5 of 25. How many times do I need to multiply in size by 5 to be 25 times as big? Well, once, I'm 5 times as big. Twice, I'm 25 times as big. So I need to multiply in size by 5 2 times. So 2 is my answer. Let's do a trickier one. Let's say log base square root of 2 of 16. Now this is weird, right? Square root of 2, that isn't really an integer. That goes on for infinity. It's an irrational number. So how are we going to solve this? Well, I noticed that the square root of 2 times the square root of 2 is the same thing as the square root of 2 squared, which is 2, right? That makes things a little easier, right? For every 2 that I get, I just need 2 square roots of 2. So what I can do is find how many times I have to double to be 16 times as big, and then multiply by 2, because to get 1, 2, I have to have 2 square roots of 2. Right, so that's something like 2 times how many times I have to double to be 16 times as big. That sounds like a logarithm. That sounds like log base 2 of 16, right? How many times do I have to double to be 16 times as big? Let's answer that. If I double once, I'm twice, 2 times as big. If I double twice, I'm 4 times as big. Double 3 times, I'm 8 times as big. Double 4 times, I'm 16 times as big, right? So this is 2 times 4, or 8. What if we wanted to rewrite this equation, this whole equation, in exponential notation, right? Now we can rewrite the square root of 2 as an exponent by saying 2 to the 1/2. That is the exact same as saying, what's the square root of 2? Right? 2 to the 1/2 raised to the 8th power equals 16. Well, we know that we can multiply these two exponents, right? So I get 2 times over 1/2 times 8, that's 4. So 2 to the 4 is 16. And as we saw earlier, 2 to the 4 is indeed 16. Now notice that to solve this problem, we just had to figure out what power I had to raise the square root of 2 to get 16. And that's the way for solving all of these logarithms. Now let's go back to our previous problems, right? What power do I need to raise 2 to get 3? Well, if I raise it to the 3rd power, I do indeed get 8. What power do I have to raise 5 to get 25? Well, if I raise 5 to the 2nd power, I do indeed get 25. Right? So anytime you're solving a logarithm, right, and you're asked to, hey, find this logarithm, right? You ask yourself, what power do I have to raise the base to get the value? And that will be your answer. Let's do a couple more examples. Let's apply this a little further. All right, let's say I have log base 6 of 1/6. What power do I have to raise 6 to get 1/6? Well, notice that 1/6 is a fraction, and I know that if I raise any number to a negative power, I will get a fractional answer. So I notice that the denominator here, right, that's just 6, or 6 to the 1. Right? So if I raise 6 to the negative 1 power, I will get 1/6. And since the answer to these problems is what power I have to raise 6 to get 1/6, then my answer is negative 1. Let's do another one. Let's say log base 4 of 2. What power do I have to raise 4 to get 2? Well, 4 is 2 squared, right? 2 squared raised to some power x is equal to 2, which is the same thing as 2 to the 1. All right? So there's some value x right here where 2 times x is 1, right? So that these exponents match. They're equal. Well, I can do some simple algebra and divide both sides by 2, and I get x equals 1/2, right? So I need to raise 4 to the 1/2 power to get 2. Let's check this, just to confirm, right? 4 to the 1/2, it's the same thing as the square root of 4, which is indeed 2, right? It is indeed 2. So I know my answer for this problem is indeed 1/2. And that's the basics of solving for logarithms. I hope you enjoyed, found it helpful. Have a great day, evening, morning, night, afternoon, and have fun. Thanks for watching.